Yesterday we completed certain topics, है ना? Electronic effects, inductive, electronic effects in which aromaticity, inductive, resonance, hyperconjugation, right? These all we have completed. Today my target is reaction intermediate and acidity basicity. During this, I will also try to consider somewhere that hydrogen bonding effects also covered. Okay, this is my attempt. If I could complete this much part today, tomorrow I can go for Toto and one class full for chemistry in everyday life, complete revision, or maybe two class if required, as we can get as other centers and all of you have time. But this is what our plan is. Today's lecture, this is our Tuesday. Toto we'll try to complete on Wednesday as much as possible. And this is our Thursday plan. If something left and if you want, okay, repeat again because repetition is the only key. This is our Thursday, Friday, Saturdays you have exam. So Saturdays probably we may not have the class. All right, so let's start. Now, the syllabus, this homolytic and heterolytic bond cleavage, I'm starting from this site. Okay. So, fission of covalent bond. If fission of covalent bond is to be considered or is to be done, you already know that there are two types of fission for a covalent bond, right? There are two types of fission. You can have a homolytic and heterolytic bond fission. So we have either homolytic bond fission or heterolytic bond fission. Of course, all of you are aware that when A and B, one is forming positive, other is forming negative, and there is no fixation that this has to be this way only. When I don't know what are A or B, so both possibilities are there, right? In case of homolytic, all we can say is that AB will be broken as A dot and B dot, and free radicals are formed, right? So if I talk for carbon free radical we have to discuss today, which are formed by homolytic bond fissions, plus and minus species of carbon. So here we will discuss about carbanion and carbocations are formed. This point we'll discuss here, right? This is our overall plan. Now, what are reaction intermediates? So reaction intermediates are such species which are formed during the reaction and are consumed there itself. Okay, so they are such species which are formed during the reaction and are consumed there, in the reaction site itself. ठीक? Of course, stability, if is high, then I will say ki more stable will have, not the inverse, more stable ones will have more half-life. Half-life, that is, they will survive for longer time, right? Stability zyada, half-life zyada. Now, stability will depend on different factors, those factors which we studied yesterday. And it is not right to compare a carbocation with a radical or a carbanion with a carbocation. That random comparisons are inappropriate, but we cannot say anything. Once in mains, this random comparison came, but like 1 in 1,000 time case, you should not take it as a generalized effect. Always compare radical to radical. carbocation to carbocation, carbanion to carbanion. Yes, there is not a condition that only these three intermediates are formed. That is free radical, yes, of course. Then carbocation, carbocation, and carbanion. And carbanion. But in this week 2 of our revision plan, these three are to be considered, and the others, which are the others? Carbene, nitrene, and benzene. These three are not this week's syllabus. So this we are not doing. This portion we have to complete. And if you consider the overall JEE syllabus chemistry also, you will find that primarily these are the topics. These I mean, as we have just mentioned, radical, carbocation and carbanion is what there for our syllabus. Okay, so हमें इन्हीं पर ज़्यादा ध्यान देना भी है for JEE, and that is what we have to cover. So let's start individually. Yesterday we have already done electrophile, nucleophile. So again, I may use that terminology today. Wherever I need that carbocation is an electrophile, carbanion is a nucleophile, I may need that terminology. Going one at a time, let's start. First one is carbocations. Okay, first one is carbocation. Of course, we will revise everything, but this is what is a final concluding factor that you have to remember. Okay, how it is reached and what it is, I will tell you everything as much as possible to complete in our designated time, but this is the portion which is important, and we'll come back to it again in the end. Okay, we have to come back to it. Now coming to carbocation, what is a carbocation? So I can say carbocation, yani R plus representation, is positively charged species. Anna is a positively charged species having positive charge on carbon. The plus charge is on carbon. ठीक? As its octet is incomplete, so it is an electrophile, and there is no fix that always this is the only way or only type of carbocation. What I want to say is carbocation could be something from alkane. You can have something from toluene type system. Yes. You can have a vinyl cation. Stable or not is not I am discussing. I'm saying all these are carbocations. Need not to be that only any specific sp3 parent say we are forming a carbocation. No, it could be from sp3 parent, sp2 parent. Okay. Again, here also this is sp2 hybridization of plus carbocation. And you must have noticed that I am not using the word carbonium ion. Okay. IUPAC has discarded this. Why? Because as per IUPAC, this IUM suffix is to be used only when there is increase in covalency of central atom. Right? When they allow us to use the word ammonium, then NH3 becomes NH4 plus. When we use the word hydronium, then it is H3O plus. When such things are possible, then only we can have the word IUM. And by this logic, we expect something like this, that a methanonium ion should be somewhere existing, penta-coordinated positive carbon. That is what should have been in sync with this terminology. But as you know, this is not normal. This is found under certain very rigorous or extreme conditions. Otherwise, no. And this is what actually we want to refer as a carbonium. So instead of the word carbonium, now we use only one thing, that is carbocation. Okay. And here only if I mention generalized version, 1 degree carbocation, 2 degree carbocation, 3 degree carbocation. Yes. There is a possibility of an aromatic carbocation, cyclopropenyl carbocation. You have very important quasi-aromatic one more carbocation called tropylium carbocation. These are important carbocation. है ना? Tropylium carbocation. If I say out of these hybridization, this is sp2, sp2, this is sp, this is still sp2. Please remember, this plus is not an sp if it is on phenyl. Otherwise, the structure will not exist. Okay, sp2, sp2 for all of them. They are all sp2 carbocations. Okay? Then there comes a very important and a very famous case of carbocation, CH2 plus, cyclopropyl methyl carbocation, which shows a very different, wait Muhammad, I'll ask you to speak, wait for some time. So there is this dancing resonance thing, okay, which is not very common. It is a particular or a fixed case that is observed here and will definitely impact some of our reactions. So you should know there is something called dancing resonance in this cyclopropyl methyl carbocation. Yes, Muhammad, please unmute yourself if you can, or I will. Just raise your hand again so that I can locate you. Yeah. Okay.
Excuse me, ma'am.
Yes, Muhammad.
Ma'am, can you just explain that benzyl case again? How you get an sp2?
Okay. So in case of this, let us take what are my two possibilities. Okay, I have to add page for explanation. Now we are ready with extra pages. Dekho, not only to Muhammad but everyone, please see. Now, what are my two choices? And you all are aware that hybridization is a hypothetical theory. So one of the sp2 is here for bonding, one sp2 for this side bond, and one sp2 is empty in which this positive is there, is my possibility number one. Here I am assuming that my positive charge is in empty sp2 orbital and the p orbitals are involved in this pi bond formation. Okay, what is my other possibility? My other possibility would be that if this plus is empty p orbital. Okay, if that is another possibility, then in that condition, this carbon has to go sp hybridized. If it is sp hybridized, then how will it be like this? Linear. These angles should be 180 degree. And here the angles kitne hai bachche? 120 degree. Right? If it goes 180, just imagine that this bond goes 180. So this ring will not survive. Not possible. So if that particular thing exists, we interpreted that it is an sp2 carbocation. I hope it is clear to all. Okay, okay. I have got confirmation. Okay, Arma. Oh, it's Arman. Fine. So others also, this is how you can ask the doubt. Just raise your hand and wait. I can see you sometimes on screen and sometimes may not. So I'll ask you to wait. Abhishek Singh. Yes, Abhishek. I have allowed you to unmute. Please speak. Okay, I'll continue, Abhishek. If you have a mic, then it is okay. If you don't have a mic, then I won't be able to help. Okay. So Abhishek was there to ask but could not unmute. So let me continue. Okay, otherwise we'll not be able to complete our theory. So this is how all these carbocations are. Here only, when we were doing dancing resonance, one more thing I want you to note. In case if I miss out on it, on any doubt, because I am having 100 plus students in my class, and if I start entertaining all doubts, then I won't be focused on this content. And the content has to be very, very focused, should not be left anything. And you know in how many actual weeks you have completed this in phase 1. So please keep note of your doubts. Okay, एक note आप बना लें. Please keep notes of your doubt. In the end, when I'll complete the lecture, I will allow others to leave, and those who have doubt will stay back and can ask. Okay, that way we will not lose the speed and will not waste the time for all. That is another way. Okay, because मेरा flow भी बार बार नहीं टूटना चाहिए. I have to be very accurate, है ना, क्योंकि इतने सारे बच्चे हैं और किसी का नुकसान नहीं होना चाहिए. So PH3C plus, I was saying कि one more carbocation you should know. And what I want you to remind here is it is known for its propeller shape. Okay, it is not something planar, completely planar nahi hai ye. This is not a planar. The 3 rings on carbon are light tilted. Okay, they are slightly tilted like fan. So it is stabilized not just by resonance. We call it that it is stabilized by its loss of complete planarity. It cannot react that easily. Yes, me, please keep your doubts to yourself. Make a list. I'll come back in the end to you. Okay. Then one more thing that you should know is something called Bend's rule. Okay. Bend's rule में आपको क्या याद रखना है, that a bridgehead won't be able to have planarity, and therefore such carbocations will be unstable, and you should not have them in your reactions involved. You should avoid their formation. But in this process, do remember that if any of the bridge is 0 and others have more than 3 or more carbons in the bridge, at least one bridge, here the 2 bridge have 4, then this plus is stable. Okay, this is not stable, but this is stable. That you need to know. I hope this part is correct. Till here, no problem. Moving to the next subtopic, that is how to define the stability of carbocation. Of course, as we have yesterday done, this stability will be directly proportional to electron donating groups, whether the resonance is there or plus I is there or plus H is there, whatever, है ना, and is inversely proportional to electron withdrawing groups, is inversely proportional to the percentage S character in the carbon bearing positive charge. This positive charge bearing carbon should always have least possible percentage, least possible percentage S, because higher the percentage S, unstable will be the carbocation. sp2, sp, if you get somewhere, they will be the unstable carbocation. One term that may come across is called cyclic, or I should say non-classical carbocation. Non-classical carbocations are those in which plus charge is not exactly on the carbon, but the species behaves like carbocation. Let me exemplify. Cyclic halonium ions, cyclic oxonium ion, cyclic sulfonium. You can have something like this type species. So all of these, cyclic halonium, cyclic oxonium, cyclic sulfonium, or if you remember, there is a reaction called oxymercuration demercuration, or in Kucherov, how this Hg single positive OAC in OMDM, oxymercuration demercuration, this species is involved, and such other species which could be called non-classical carbocation. Okay. Now, what will carbocation do? So, of course, they are electron deficient. So, reactions, they will act as electrophile and can attack on any electron dense systems, be it benzene, be it any negative species as in SN1. They can undergo eliminations. Example, dehydration of alcohols. That is one possibility. Yes, they can undergo rearrangements, which I'll try to revise in 2-3 minutes at least. I will dedicate for rearrangement. Okay. So they can act as electrophile, do elimination, undergo rearrangement, or can undergo redox. Now, what is redox? C plus can accept one electron and become a radical. That is a possibility. Can further accept one more electron and can become a carbon ion. So it is possible. Now that depends on reaction to reaction, whether this will take place or not. But yes, that is possible. Okay. Now coming to the most important and the usually I would say some people may have confusion that rearrangements, what we have to remember regarding rearrangement in final stages of exam. For rearrangement, beta, always remember a very, very important line that rearrangements have to be, as a rule, only and only intramolecular. It is never possible that an atom or a group of atoms shift from one atom for one carbocation to another. It is entirely intramolecular. Take again as a rule, always only 1-2 shift of groups will take place. That is also compulsory. Not more than that. 1-2 is all you can have. I will exemplify. Wait. Okay. If any chiral group is migrating, it will show retention of configuration. That is also a compulsory rule. Okay, if there is any chiral center migrating, it will show retention of configuration. Okay, last is the migratory aptitude of various groups. That is, I think spelling needs to be aptitude of groups. So we usually have, as per our syllabus, H and pH are neck to neck. Then comes the 3-degree alkyl. Then comes 2-degree alkyl. Then comes 1-degree alkyl. Then comes methyl. So in general, I can say presence positivist presence of electron releasing groups increases the migratory aptitude. Okay, and this whole thing is called Wagner-Merwin rearrangement. इन्हीं को हम Wagner-Merwin rearrangement कहते हैं. ठीक, and always as a rule, new carbocation should be more stable than original. This should also be followed. If the new carbocation is not more stable than the original, then this entire shifting thing will not be of any use or any purpose. It will not be possible. So compulsorily we need a new carbocation form should be more stable than the previous one. Is that okay? See? So coming to few examples. Now, what are the examples? Let me, one more thing I should first mention, that amongst phenyl rings, again we'll say EDG groups at meta and para positions increases migration. ठीक, but any type of group, whether it is ERG, electron releasing, or electron withdrawing, any group at ortho position always decreases the migratory aptitude of the ring. Migratory aptitude of the ring. This is compulsorily always when electron withdrawing groups are there or releasing groups are there. This is found always. For example, when we took an example in which, see here, I have different rings, OME, okay, OME, ring, and so on. Such experiment was done and it was found, observation agar main kahun, if I can say observation, para-methoxybenzene, okay, para-methyl, then no substitution, then Cl group laga hai, and then comes ortho pe group hai. Okay, if I compare migratory aptitude of these, the order is like this. Okay, इस तरह का order पाया गया. So you can understand how difficult it is for group to migrate from ortho position. If I could add a numerical value, see electron withdrawing group से भी हुआ है, अगर इनका relative ratio 500, 15.7, 1.7 and 0.3 is what their relative ratio of migration was found, which is extremely alarming that OME is such a good electron releasing group. Then also its migratory aptitude is so least. It is found to be so less. Okay. So this you should remember and never forget that yes, H can migrate. So D can also migrate. Deuterium is there. D can migrate. Never get confused that whether D can migrate or not, D can very well migrate. There is no problem. But I'd like to add a small point that even there are different type of rearrangements. Okay, there are different types. I mean, in some, the carbon skeleton may change. In some, carbon skeletons may not change. Okay, so those in which it will not change is allylic rearrangement. Allylic arrangement is very much like allyl resonance. This resonance, if in a reaction, position of attack is found to be different, then it is taken as allylic rearrangement. Yes, I know it may be difficult to digest, but it is there. A 1 degree carbocation like this shifts to this. See, carbon skeleton is not changed. The carbon skeleton remains same. So that is one type of rearrangement. Carbon skeleton is changed. Yes. For example, this neopentyl carbocation, methyl shift is observed. This is my new carbocation. See, entire carbon skeleton is changed. So that is one possibility. As I told you that it has to be 1-to-1-to shift. See, from this position, I can go to this position. I know that a 3 degree will be even better, but you cannot jump directly from first position to third position. You can go n number of times by the 1-to-1-to method. That is allowed, but you cannot rearrange directly from position 1 to position 3. This is good. But in case if you think that 1-3 shift of methyl, then it is absolute no. This will not be formed. Never. It is always going to be 1-to-1-to. For this, you are allowed to have 10 steps, 10 times rearrangement. Well and good, no objection. You can do that. But a jump to third, never, ever. Is that absolutely okay? And I hope you have remembered that retention of a chiral center. This is not just with carbocation, almost in every possible rearrangement, be it carbene, be it nitrene. आगे चल के भी you may come across with this terminology, retention of configuration, that you may find useful. Now, one thing more that sometimes children do a little confusion is ring expansion, ring contraction. Just contraction, just few important examples which can affect your general understanding. Again, whenever you talk of ring expansion or ring contraction, it has to be 1-to, not if this carbocation was, say, like this. It is 3 degree. It will not come to 2 degree, na? And you cannot have a jump like this. No. This is not allowed. From here, you can have one-time shift. Very well, no problem. And you can have a new carbocation. This is allowed. You can have a multiple times rearrangement. See, if I say this shifts, very good. If this shifts, Hamesha, I personally do this numbering. It helps me to locate where am I heading. 1 will be now connected to 6. 6 will have 7. 1 say connected 2 hai, plus charge will now be on here, right? This type of shift is there. 3, 4, 5. Now you may argue that if I would have shifted 3, then after that a 3 degree carbocation may be obtained. Yes. But each step, there and there you have to decide. Like I wanted to say that here, this is a 2 degree alkyl group which is migrating. This is a 1 degree alkyl which is migrating. So for major, I will prefer shift of 6th carbon rather than the 3rd carbon. So this will not further shift. Okay. So more and more example I'll take. Don't worry. if I have this carbocation, let us see now this, and here I shift, I think I will get this. This can again shift to 3 degree. Yes, very well, no problem. You can shift n number of times, but the point remains a new carbocation has to be more stable than the first one. A very, very famous example of something like this. Carbocation if generated like this. Then I will have first shift of this. So when I will have a shift, then here I will have a carbocation. I hope you are getting it, or you can write position 1, 2, 3, 4 to practice. Again, with respect to this ring, this is just on the next carbon. So I can have one more shift. Okay, I'll take one more shift. And I think I will have this carbocation. I guess you all are getting this. So I can go further and further this type of rearrangement. That is okay. Clear? That is allowed. But on the same, like on the side that after 1 or 2, you will get a better. So compromise at any step is not at all allowed. Okay. Ring expansions. You will observe ring expansion from 3 to 4, 4 to 5. Okay. 5 to 6. Rarely 6 to 7. Always. This is a very, very favorite case in pinecolone rearrangement. There, this is the most common. Okay, there आपका pen shouldn't stumble. 6 to 7 is a very important rearrangement in pinecole to pinecolone. वहाँ मिल जाएगा. ठीक? Here, 3 to 4 thing is also important to know this. Okay, this can rearrange, but there is an equilibrium between the two. Okay, these are very, very comparable, and you can certainly not ignore any of these in your option. Okay, this is almost 51% yield of product comes from this, 49% yield of product comes from this, but never will this rearrange to this. That you remember. Never ever rearrange to this. Okay, it only rearranges with ring expansion, contraction, expansion, contraction. This is the, in fact, out of the two important examples of contraction, one is this one only, that if I have a plus like this, then like this, for a dancing resonance, it may undergo contraction. We don't, as I said, not many example of contraction. This is an example of contraction. And as I have already told, reversible, both ways reaction give comparable and competitive product. See this, okay? This also shows contraction. From here, it goes like this and positive. And yes, it can rearrange to this carbocation, 3 degree. Okay, so reversibility is observed either here, okay, reversibility in carbocation rearrangement. Example 1, जो भी ऊपर है ये वाला, okay, this one I am talking, and the only other is pinecolone rearrangement. Otherwise, in carbocation reactions, you will not find carbocation rearrangements, you will not find anywhere else any such rearrangement, reversibility. Now, pinecolone, I am assuming that everyone remembers. It is not in this week's syllabus, don't bother. But just कि आपको लोड ना रहे कि क्या बात किए थे, क्या था. This is I'm talking. This was some reaction in which pinacol is rearranging to pinacolone. This is the only reaction where carbocation rearrangement shows reversibility. Okay, so these are the few cases, 2 cases where carbocation shows reversible rearrangement. Otherwise, you will not have any such thing, right? Now, after concluding all this, I in fact wrote on a very initial page somewhere. Where are we? Carbocation. I want to discuss the final stability. This we have done. Conclude करना है for carbocation stability. Yeah, here. So after concluding all this, please see this. Very important point. Why this is most stable. Complete octet carbocation, yesterday also I told, is very, very stable, even more stable than 3 degree. Okay. And then comes PHCH2 plus. 3 degree, then PHCH2 plus. See, this is 1 degree benzyl. 1 degree benzyl is more stable than 2 degree carbocations. Okay, but 3 degree carbocation is more stable than benzyl. If I had a 2 degree benzyl, PH2CH plus, it would have been more stable than 3 degree. Right? See, this is allyl resonance, but it is primary. It is primary, right? So, where it is located? It is more stable than these. These are very, very unstable carbocations. What I wrote here, if the degree is same, this is also 1 degree, this is also 1 degree. Okay, they are of same degree. But if one can rearrange to more stable, take it as higher in stability. Take it as higher in stability. This I hope you will remember. The one which can rearrange will be higher in stability of carbocations. Okay, now let us move to carbanions. This was carbocation entire discussion. Now we are coming to carbanions. Again, of course, carbanions are C minus species. Okay, they are C minus species. And we again have to think what are their factors and how to use them, right? How to generate them. Let's first talk for them. So they are formed by hydrolytic fission. That is, of course, there. Let me directly come to their types. So it could be a primary carbocation. It could be a secondary CH minus. It could be R3C minus. Yes, there could be resonating carbanion. And this particular is more important because it is not just resonating, a very good case of resonating aromatic cyclopentadienyl carbocation. Something that is just resonating, yes, benzyl carbocation. I can have allyl carbocation as a case of just resonance. You will have a d orbital resonance in CCl3 minus. CF3 minus stable, but no resonance because fluorine will not have empty d orbital. Okay, CH2 double bond CH minus, CH triple bond C minus, and again phenyl directly here. All these are different cases of carbanions. Okay, now the point is again coming to what is their hybridization, right? Generation, of course, we have said that it can be formed by all of hydrolytic fissions and all. Let us see what is their hybridization. So I can say all of these are sp3 carbon ions. And so will be a bridgehead. Let me write it as a separate. That bridgehead carbocation cannot be stable, but a bridgehead carbanion is very much stable as it is sp3. Here, if I talk this, what should I say? This lone pair, one H is there. So here, this carbon is sp2, but this negative charge is in p orbital. Is that right? And this will be I saw some chat or something, but I don't know where to see. So I can't. Could you, someone share the what? Unmute yourself and tell. I could not read you. You have kept it as your name, but it is not showing me. Okay. It is difficult to find someone in this. Arey, mere pyare dhakkan. Ma'am, could you please share the notes after the class? Yesterday, I also sent it to central office and they will forward it. They are always shared. Hannah, you have to tell your admin to contact to central office Prasad sir and they will share. Okay? अभी पहले जो सुन रहे हो वो उस पर ध्यान लगाओ और जो तुम लिख सकते वो लिख लो. Whatever you can write, you write. I will definitely share this. May not be very beautiful, but whatever it is, it will be shared. Okay. One more. 2263 Ray. Tell what is the issue. 2283. Unmute yourself and tell if there is anything important. Has to be important.
Ma'am, could you please tell me that which lesson is going on at present? Sorry for disturbing.
You are asking which lesson?
Yes, ma'am. General organization.
Phase 2 schedule is shared to you?
Ma'am?
Phase 2 is going on in your campus? Revision phase?
Yes, ma'am.
Yeah, so revision phase this week, organic topics are GOC. I am doing reaction intermediates.
Okay, ma'am. Thank you.
Okay. So coming back to where we were. So so this is resonance. So I'll keep this in P, but it is sp2. I think same story for this one also. This is lone pair is in p orbital and the hybridization is sp2, and same story to this also. And whenever there is a resonance, here my negative charge in p and hybridization I will call sp2. Here there is no resonance, so it is in sp3 orbital. sp2 hybridized, sp hybridized, as we have discussed sp2, and this is sp3 carbanion. Okay, so you have to be just cautious that even if it is sp2, this electron pair is not in sp2. And remember again, pH3C minus, yes, it is said to be sp2, but propeller shaped. Okay, it is not planar. It is propeller shaped carbanion, like the carbocation. Same story again. Okay, next let us talk of stability of carbanions. So carbanions are electron rich system, है ना? So their stability will be directly proportional to electron withdrawing groups, inverse to electron donating groups. More percentages in hybrid orbital of carbon having negative charge, then also the stability of this carbanion will increase. And certainly if your carbanion is aromatic, that this aromatic we missed in carbocation, but I discussed tropylium cation. So I hope you understand that if that positive charge is part of aromaticity, it will be stable. Okay, you can have a possibility of this reverse hyperconjugation also, like CCl3, this type of hyperconjugation also stabilizes carbon ion. This is minus H, reverse hyperconjugation I'm talking. Now, when I said presence of electron withdrawing groups, this is what I started here when we just started carbocations, carbon ions. Where is my carbon ion? I just started carbon ion. There was a stability order. Let me see where is it gone. This was all carbocation we discussed. Carbocation stability. My order of stability of carbon ion page is, I have to arrange all this. I have jumbled them here and there. Here. So, see electron withdrawing groups. Now, what is this pK? I want to say pK is when there was H attached to this negative side. pK of their conjugate acids I am talking. Okay, so this minus when had H, that acid, conjugate acid, pK4, ठीक, two side carbonyl 8.8. So I can say higher pKa, it means lower K, right? And lower Ka, it means it is a bad acid. It means there is a lower stability of this anion. है ना? Ka ज्यादा है, इसका मतलब ये ज्यादा स्टेबल है. So stability. So comparison, if I do, this is the most stable. Is that clear? This is the most stable carbon ion out of these three I have mentioned. Then comes this one, because 8.8. Then comes this one. If I tell of different groups to be present adjacent to this minus, it is clear that nitro is making it most stabilized. Then is the carbonyls one. Then there would have been ester, SO2, CN, amide, halides, H, and then alkyl will be the least. This is the order of the groups, if present adjacent directly attached to CH minus, how they will stabilize them. Okay. After doing all those things, variety of comparisons, I can say the stability is in the order cyclopentadiene with pKa 16. See, this is more stable than sp hybridized carbon ion. Please take a screenshot in your brain directly. Okay, and sp is more stable than pH 3C minus. pK values are the evidence 16, 25, 33. Then comes pH 2CH, pH CH2 minus. Allyl is less stable than benzyl, right? Then they are almost somewhere close by they are going, but this is how we place them in the order. 30, this phenyl, vinyl. After vinyl is the methyl, 1 degree, 2 degree, and 3 degree. Please take screenshot of this page. Still, I'll share the note, but still take. If it reaches or not reaches to you, take a screenshot. Okay. So let's move further. So after this whole carbon ion stability, there is no rearrangement in case of carbon ions. So that is not much of our concern that carbon ions can rearrange. So no, carbon ions can never rearrange. Carbon ions will not, just wait, let me put it at its, अरे रुक जा भाई, I guess closest possible I have got. This is where I need it. So, as we have said that this is how they overall have stability. And rearrange. So, honge nahi carbon ions. So, we don't have that topic here that will they rearrange. They will not rearrange. Take. Now, if they will not rearrange, it is good for us because usually rearrangement is not something that we are very fond of, right? Rearrangement हमें कभी भी बहुत easy questions generate नहीं करता, so we don't like much of rearrangement. But what other reactions they can give? What other reactions these carbon ion can give? So I will see they can act as base and give acid-base reactions. Yes. For example, RMgX plus water, we say formation of RH, that type reaction. They can act as nucleophiles, right? And participate in SN2. They can participate in SNAR. जाके attack तो कर ही सकते हैं as a nucleophile. So yes, they can act as a nucleophile. They can attack on SNAE on acid derivatives. So all these possible reactions, they can participate as a nucleophile. Okay. So that type of reactions, they can go for redox. Again, as I have just mentioned in carbocation, just opposite. This started losing electrons. So it will form first radical, again lose one more electron and will form carbocation and so on. Right? So they can go for redox. That is also possible. Clear? There is no example of dancing resonance case here. So that is not here. Rearrangement is not here. All those things which might be a little, elaborative to remember and all those things are not part of carbon ions. So there we are relatively at a shorter topic. Moving to next is the free radical. Now, when I talk of free radicals are basically species having unpaired electron. Okay. Any species that have unpaired electron will be referred as free radical. It could be any species, need not to be just carbon. You can have RO dot, which is alkoxy radical. You can have Cl dot, which is chloro radical, and so on. But currently we are talking of carbon radical. Carbon free radical. They have one unpaired electron on them, so they will behave paramagnetic, right? And can be of so many further types, as we have said, 1 degree, R2CH dot, R3C dot, CH2 double bond, CH single bond, CH2 dot, same way, phenyl dot, benzyl dot, and so on. A very important point that you need to notice is shape and hybridization of radical cannot be defined as a fixed one. Again, as I said, hybridization is a theoretical concept. So radicals can be sp2, radicals can be sp3 also. It depends, whatever stabilizes them. And it has been found that if we increase the electronegative atoms on this C dot. Okay, as we increase the electronegative atoms on C dot, its hybridization shifts from sp2 to sp3. This is clear sp2, this is clear sp3, and these are somewhere intermediate between sp2 and sp3. But radicals can be sp3 is such an important point, because now bridgeheads can form radical, because then it will be sp3 radical. This dot will be in the sp3 orbital. Okay. But if I talk of resonating PHCH2 dot, now this dot is in p orbital, and hybridization of this carbon is sp2. So it has a flexibility of going both ways, but as it can be sp3, so bridgeheads are now possible. Whenever such species which could not form, planar, see this dot, this is sp3, this becomes sp3 and is found to exist. Okay, and again repeat, pH3C dot is again sp2 but propeller. sp2 hybridized carbon, this is in p orbital, and this is propeller shaped radical. Clear? Whenever you are asked to compare the stability of radical, stability, this time I will not be able to say electron releasing groups are stabilizing or withdrawing group are stabilizing. In fact, it is found both electron donating group and EWG groups stabilize radical. This time we cannot say so. And stability always is considered by bond dissociation energy. Whenever any bond dissociation energy is given in the question, every time BDE word, if not mentioned for the generation of carbocation or so, is always taken as homolytic bond fission. Particularly for carbon hydrogen, specifically is taken as homolytic bond fission. And as I said, that higher the bond dissociation energy, it means less will be the stability of that radical. And less stability, matlab, if it is stability is less, it means its half-life will be less. Let us see this. This I have taken from standard Jerry March, okay, from different tables from that book, and I have tried to mark it for you. Take 1, 2. If I see this table, right hand side, I am first seeing this. D is considered at energy, at bond dissociation energy at 298 Kelvin. Here is the kilocalorie, here is the kilojoules. Here it is only kilojoules data. Okay. So I said more the bond dissociation energy, unstable the radical is. So if you see, highest I got a 544 for this one. So I kept it as the least stable of all. Okay. Then second number I got is PHH 464. See it here. It is second stable. Similarly, if you move, third is methyl. Okay, so here it is. This is how I have carried out this comparison. Yes, methyl is less stable than vinyl. That is there. If you will come somewhere here, vinyl 431 kilojoules and methyl is 439. So it is like this. MECH2. Where is MECH2? Here is MECH2, number 5. I got it at number 5. Then 410, 2 degree. Then 3 degrees more stable. I'm going in a decreasing order. Decreasing order matlab I am going from less stable to more stable. 7. Now I am finding 8. 8th. Here is 8th. Okay, see, this is more stable than 3 degree. And what it is alpha. This is the alpha position to carbonyl. So that is why I said both withdrawing and releasing groups will stabilize the radical. So this is stable. कहाँ गया वो? ये रहा 8th. And nearly same stable MEC double bond CH2H, है ना? And ETCH CHOET MEH. This is also similar. Okay. Then I got benzyl here 372. Yeah, 9th. 10th I have got 2 cases. 1 and 10th this. So I was more interested in allyl. And then 11th, the most stable is alpha to cyno. Is that clear? To add some more cases, I took this, but I didn't want you to get confused. So I just added this. Some of you might have taken the screenshot of this data just so that you can realize how questions can be created. Okay. Here again, see some which are not there. Cyclopropyl radical ke bare mein. So it is like vinyl. That is what you can conclude. Okay. So that is why I added this also, just to give you a general outline of how they behave. So most stable alpha 2 electron withdrawing groups and allyl, benzyl, alpha 2 carbonyl, 3 degree, 2 degree, 1 degree vinyl, methyl, phenyl, and then percentage S is the worst of all. High percentage S. Itna percentage S isme zyada. This is not capable of forming a stable radical. Again, as we go into radical, we do not have any, what should I say, rearrangement and that type of reactions. So that is not a problem. They are formed by homolysis, which could be achieved either by thermolysis or photolysis. Photolysis, whenever on a reaction you come across H nu, okay, take radical reaction. It is a radical reaction. That is a default understanding. Or if on the arrow you come across 300 degrees centigrade or high, then also you take radical reaction. These are the temperatures which are like pyrolysis and conditions where they generate radicals. Okay. Now, what are the reactions given by radical? How they will behave? First and foremost is their combination. Okay. I will say radical combination. Direct combined with each other is the zero activation barrier reaction. CH3 dot combines with Cl dot and form CH3Cl, this type of reaction. Okay. Of course, this combination, if I talk, then I would say methyl is best. Then it is 1 degree alkyls. Then it is 2 degree alkyls. And then it is 3 degree alkyls to do this radical combination. Then comes the radical disproportionation. Yes, Mazhar, please keep your doubt to yourself. Write in some notebook and in the end, I'll let you ask. Okay. So what is radical disproportionation? Like this CH3, CH3. So another radical which could be same like this. So it attracts this H and you have alkene and alkane form like this. This is what we call radical disproportionation. And the disproportionation order is 3 degree radical, then 2 degree and 1 degree. Methyl, of course, not in the race because there is no beta H possible. Okay. So as I said, radical combination is the best, but note, very important, PH3C dot never combines to pH3C, pH3. Never. It never combines because due to steric. Okay, as I said, steric kam hona chahiye for this combination, which is not possible. It combines from one of its resonating structure from this position. When it comes to this position, then C dot pH3 can come. So their radical combination product is like this. Okay, not what we could expect. And similar is the case with pH, pH O dot. This is also very, very stable. And the reason of stability is not resonance. Stabilized due to their failure to combine. And reason? This only, steric. Due to steric, they cannot combine. Okay, so they can have radical combination, radical disproportionation. Third reaction is there redox. I have already discussed redox so many times. And fourth, they can attack on double bond or CH to generate radical. Right? For example, anti-Markovnikov of addition on double bond, how Br dot adds and a new radical is formed. Halogenation of alkane, how a new radical is formed. So that type of thing I'm saying is possible. Clear? So this was about general radical things, and I will go back to conclude the stability of radical. This again, because this is important. So radical stability you will conclude by homolytic bond fission. Why I'm so emphatic is because there was a past JEE question on this topic. That is why I'm so emphatic about this radical thing. Let me show you 2021. Why I'm so emphatic. There was a comprehension in 2021. Let us read. Please excuse the numbering. It is from my notes, so I just left it as number as such. I think that is not a concern. The content should be the concern. The amount of energy required to break a bond is same as the amount of energy released when the same bond is formed. In gaseous state, the energy required for homolytic cleavage of bond is called bond dissociation energy or bond strength. Bond dissociation energy is affected by S character of the bond and the stability of the radicals formed. Shorter bonds are typically stronger bonds. Okay. BDEs, yani bond dissociation energies for some bonds are given below. CH3C, ClCl, CH3Cl and HCl. Correct match of the CH bond CH, which are shown like this. Okay. Is that clear? That these bold bonds are to be considered in column J with their BDE in column K. Now we have to match these energies. I'll wait for 30 seconds and we'll have a sip of water. Meanwhile, please match it and I'll show you the answer then. Yes. So as we had seen that percentage as highest was the worst in our list. Okay, so same thing will continue. This is number 1. And I will not go by data. We'll simply see that this is the worst of all. So this is number 1. Is that clear to everyone? है ना कैसे किया अपन ने? Right? Just wait. So this is number one. Then benzyl was stable, right? This is 2-degree radical. So amongst all, this seems to be the most stable one. So the least BD we'll give to this 4. Q को 4 दे देते हैं, S को 1 दे देते हैं. Now comes the vinyl and this. So vinyl will be unstable. So this should be given 2. And vinyl is unstable. So इसको मैंने second highest दे दी. And now the third highest should go to this. So we are getting P को match 3, Q को match 4, R का match क्या लिखा है मैंने 1 लिखा है 2 लिखा है I guess 2 लिखा है and S का match is 1. Let us check 3, 4, 2, 1. It seems first one ही answer आ रहा है. Let us, this was question number 32 in my draft. Let me show you. What was the number? 32. 32A. Okay, 32A. So this is the question I was preparing you for. More the BTE, less is the stability. Its second question is not for this week's syllabus, so I'm not asking you to do this, but this was the other half of that paragraph. The correct statement, which is reaction initiation and all that is not for this week. This part is for this week. Okay, so I hope that is absolutely clear to all. And that concludes our reaction intermediates. I'm jumping to acidity basicity directly. Okay, after 8, I'll ask you to share your doubts and then I'll entertain doubts. So if I go to acidity and basicity, initial things I have written, which I'll share as a notes to you, but I'll not discuss much in the class, like Arrhenius concept, Laurie-Bronsted, important difference between Arrhenius, what are the drawbacks, and a Lewis acid base. This is my general, when I explain, I can say Arrhenius theory. All those acid or base which can be explained by Arrhenius can be explained by Laurie-Bronsted. All those which can be explained by Laurie-Bronsted can be explained by Lewis theory. Like that, I wanted to say. Conjugate acid-base concept, right? They are always at a difference of 1 H. I'll share the notes, so don't worry. You can go a fast reading then. H2SO4, conjugate base is HSO4 minus. HSO4 minus sulfate. So there has to be difference of only 1 hydrogen. Can't be a difference of 2 hydrogen. SO4 2 minus is not the conjugate base of H2SO4 here. This also I have added. It's not the conjugate base of H2SO4, right? Then in a conjugate concept, when we say, then always if one acid is strong, then automatically the other acid will be weaker. That is a rule in a conjugate concept. If acid strong, then its conjugate base will be poor. If base is strong, then acid will be poor, right? These all things are shared because ultimately K and KB, or for a conjugate pair, always end to KW. That is why. Okay, thus in a conjugate pair, if acid is strong, the base will be weak and vice versa. To understand the derivation of these two, you can go to these 2 videos of ours. That is possible. Those are available. You can see those. Acids with lower pKa than 1.74, minus 1.74, will protonate water completely. Bases whose conjugate acid has higher pKa than 15.74 will deprotonate water completely. Clear? Effect of solvent, of course. If there is solvent, then ionization is easier. That is considered. Okay. Now let us start our journey from here. So, number of factors that affect the strength of an acid. Most important factor is stability of the conjugate base. Because if I consider two acids, HA and HB, then H plus is similar stability. I'm only concerned about the relative stability of A minus and B minus. Okay, more stable any of these will push the equilibrium more forward. And when the equilibrium is more forward, it means that the given acid is having higher acidic strength. So more stable conjugate base, more stronger acid will be. Okay. Ka is directly proportional to the anion stability. And these anions are directly proportional to minus I. Okay, electron withdrawing. As we have just discussed carbon ion, same way, minus R, minus H, inverse to electron releasing effect. Bond strength of HA is important, right? Easier to break this bond, better the acid will be. As this could be proved from HI, HBr, HCl, HF. है Solvent could be an important factor. Take always as a rule, strong acid dissociates first due to common ion effect. And this is something which you use in your statements like H2SO4 and HNO3. I'm talking of nitrating mixture. Nitrating mixture for benzene, right? H2SO4 here protonates HNO3. Am I right? H2SO4 protonates HNO3 and then we get NO2 positive. So this acts as a stronger acid. This acts as a weaker acid. So stronger acid dissociates and weaker acid acts as a conjugate, as a Lewis base and thereby forming nitronium ion. So always stronger acid is the one which will lose H plus. See, on this concept that stronger acid will dissociate first, JEE 2003, there was a question. Okay, so these are different numbers I have given, acid number 1, 2, 3, 4. And now it is asked that only 2 moles of NNH2 are made to react. Which sites will react? So you should know how to arrange them in the decreasing order of stability of conjugate base. So if I talk of their dissociations, strongest acid is COH4. Right? Then it is the nitrophenol. So number 1. Then it is the phenol, number 2. Then is the terminal alkyne, number 3. So decreasing order of acidity is 4, 1, 2, 3. If I add only 2 moles of NNH2, then 4 and 1 will dissociate. So 4 pe I put Na plus and 1 pe I kept Na plus. If they had given 3 moles of NNH2, would have removed this one. 4 moles of NNH2, I would have then removed this one. Okay, in the order 4, 1, 2, 3, you will remove the H plus. That is JEE 2003. Now let us come to specifically organic acids. Alcohols. Certainly there is an exception. All of you remember that MeOH is stronger acid than water. Not much relevant for JEE, so I will not pay much attention to this. But yes, there is an exception. Well and good. बहुत बढ़िया बात है. Coming back to what is important for JEE. Presence of electron releasing groups will destabilize O minus, right? So ETO minus, HO minus, isopropoxide. Most stable is water. Ka conjugate base, है ना? Stability of conjugate. Then comes the ETO minus, then isopropoxide. So K is 2 greater than 1 greater than 3. Again reminding methanol, then water, then other alcohols is there as an exception, but not to be considered as such. JEE कभी नहीं पूछता है उसको ऐसे. Then comes the phenol. Phenols are acidic, all of you know. है ना, strong acid, then alcohol, because ring will act as a minus R group. Okay. Presence of electron withdrawing groups increases the acidity. Now, how you will handle the question? So, if the phenol is given and the groups given are same but at different locations, you identify the nature of that group. See, here cyanide is there. So, identified minus R and minus I is the characteristic of cyano. Minus R will use only from ortho and para position. And minus R will increase the acidity. So, ortho and para will be better acids than meta and PHOH. Okay, as resonance will not operate from meta position. So, I am leaving it ki meta and PHOH will be behind. If I talk of minus I, it is a distance dependent. Ortho will have more minus I, then the meta, then the para, then the phenol. To conclude, finally, you will say minus R dominates over minus I. First, you will consider orthopara should be ahead. But when the dominating effect confuses you with equality, then you go to second effect. Ortho and para both equal, then we'll ask to minus I. Which one will you select minus I? It says ortho is better. So you put ortho better. But then don't listen any more to inductive. Go back here. Ortho was equivalent to para. So next will be para. Nowhere meta will be there. Ortho, para. Then comes the meta. Why? Because meta and PHOH are now next set. So again, the decision to break that equality, okay, to break that draw situation, we are using secondary effect. Meta is better than phenol. Meta is better than phenol. If there is any hydrogen bonding, etc., that we'll see further. But otherwise, this is how you will end up your answer for phenols. So one case is when the group is same and position is different, then you will do this thing. If second type of question, groups are different and positions are same, that is other possibility. For such cases, very, very important point, first check within a molecule which is the acidic center. Okay, this is the acidic center. OH and CH3, this is the acidic center. OH and SO3H, this will be acidic center. This will be acidic center. Why I said so? Don't say that OH is the one you will compare and you will take the effect of SO3H. No, when you will introduce the base to this molecule, SO3H will take away the acidic reactions. So 3 is going to be the strongest. Okay, so first and foremost, when groups are varied, check which is the part of a molecule which will act as acid. And first decide on that. Now leftovers, okay, all have OH as a center, right? Now you decide on other things. Bromine minus I greater than plus R. So overall it is electron withdrawing group. This is electron donating group. And this is reference. Electron donating group will be pushed last, withdrawing better. Reference is in the middle. Is that clear? This is how you will decide. Here comes if the group is same and its number is increased. 1 nitro, 2 nitro, 3 nitro. More the electron withdrawing, better the acidic strength, picric acid it is. Okay. Now comes the H bonding. This is, let us see. Now see, H bonding does not have usually energy greater than 18-19 kilojoules per mole usually, है ना? HF को मैं हटा भी दूं तब भी इससे ज़्यादा एनर्जी नहीं है इसकी. It does not have energy higher than this, right? So if this is how its energy is, how it will impact our, properties of a molecule, like how it will impact So I will say, see, what are the different cases of H bonding? Reactant, and here is a product. I have reactant and product. First case, if I assume that there was H bonding here, and when it lost H plus, then no H bonding. Then no H bonding. Okay? Now see, when this reaction will happen, I will need extra energy to break this H bond, and in the product there is no compensation of that energy. Extra energy to initiate a reaction. So delta G is equals to delta H minus T delta S. There was initially H bonding and now there is no. So this delta H will become, this more energy is required. So this difference will become smaller if it is exothermic, or may become endothermic. So reaction will become difficult. So if this is the case, then we'll conclude reaction rate decreased due to H bonding. Example, orthonitrophenol is weaker acid than paranitrophenol, right? Because there is H bonding in orthonitrophenol. Same is the case with salicylaldehyde, is a weaker acid than parahydroxybenzaldehyde, right? Case number 2 क्या हो सकता है? When reactant has H bonding, product also has H bonding, but strength of H bond in product is more than in reactant. Okay, let us come to example कि H bonding दोनों में है, but later it is becoming stronger. Example is the COOH, COOH. Now there is already H bond here. Right? There is already H bond, but overall system is neutral. When it loses this H plus, then due to resonance, the del negative polarity on this oxygen is increased. So the strength of H bond is increased. Okay. So this increases the forward reaction. H bonding was both sides, but the product is having stronger H bonding than reactant. Is that absolutely clear? Third, if reactant has H bond and product do not, I think we have already discussed H bond and no H bonding in product to already discuss. Reactant has H bond stronger than product. Agar aisa hota to, I could not, in acid things, I could not find any such example. In base, there could be. Okay, in base, this could be, but in acid, it is not. So, but yes, again, what will happen? Then, not but, then backward reaction is preferred. अगर ऐसा है कि पहले H bond ज्यादा अच्छा है, बाद में it is becoming weakened, then it is better to go forward. Okay, last case ऐसा है, इसमें no H bond and product has H bond. Then again forward reaction. ठीक, then the reaction will go forward. Now again ये कब होगा? ये फिर से होगा base में. Base, in base we will see this example. Okay, that there was no H bond initially, but after accepting of H plus or something, some H bond is there, we may have the effect, right? So there is a possibility of such thing. So this is the effect on acidity basicity. But yes, H bond doesn't have only this effect. H bond also affect boiling points, right? Example, carboxylic acids will have much higher boiling point than alcohols, will have much higher than aldehyde ketone on a boiling point due to strong H bonding, right? There are more examples, but one I am taking here. Then there will be effect on number 2. One more thing. One more example, one more point. Intramolecular H bond has low BP than intermolecular H bonds. Correct? Orthonitrophenol has low BP than paranitrophenol. In last week, I think there was this methods of separation. So orthonitrophenol was steam distill. Steam distill. This language we have used. Okay. Third, H bond can affect solubility. Can affect solubility. Now it depends. Like dissolves like is the thing. But if something can form intermolecular H bond, it will be more soluble in water. If it can form intramolecular H bond, it will be relatively more soluble in organic solvents because it don't have to interact with solvent and thus. But I cannot generalize that as such as a statement. So not writing, but it will affect stability. Okay. Definitely kinetics of reaction. Kinetics of reactions, various reactions like acidity, basicity, and so many reactions could be affected, right? Equilibrium constants when kinetics are affected, and if it is a reversible reaction, then equilibrium constants can be affected, like tautomerism if is affected with change of solvent due to H bonding. So there are so many effects of H bonding, right? So here I have again added that if H bonding is to be taken into consideration for acidity, so you will again do the effect of nitro same way, orthometa-para, but in the end you will just see, but due to H bonding, para is stronger than ortho. But as H bonding is never so strong that it dominates over resonance, so it is never that weak becoming and pushed to last. Just among the resonating systems, it is pushed here and there. Okay, so para then ortho. It will not go to last. Okay. One more thing here I will add, then I'll go. As we have said that always, whenever there is a reaction, if I say HA is reacting with some B minus, and it is converting to HB and A minus, right? So I'll say this is conjugate acid 1. This is conjugate acid 2, conjugate base of pair 1. This is pair 1, and this is conjugate base of pair 2. Okay, so such equilibriums always shifts from strong acid and base to weak acid and base. What do I mean? Let me explain. For example, if I have alcohol and I react it with NaH. So alcohol is my conjugate acid 1. This is conjugate base of pair 2 because its conjugate is not ROH. When they react, it should form RONA. You write the complete reaction, then we'll decide hoga ya nahi hoga. And this is forming hydrogen, which is conjugate acid 2. Right? So you'll immediately check acid A versus acid 2. Acid 1 versus acid 2. So Ka of alcohol is greater than H2. Hydrogen is a very weak acid. So this is you found weak. So definitely iska conjugate base will be strong. This is acid you have found strong. So this will be weak. So this reaction will move forward. Okay. If I go to alcohol and NaOH, I do not find the strong reaction. Okay. Same is the story with NaHCO3. If this reaction would have happened, RONA plus H2CO3. Now this is a strong acid. This is a weak acid. This is a strong base. This is a weak base. So this reaction goes backward. Clear? If we are given RCOH plus NaHCO3, then you will write RCOONA plus H2CO3. Again, you will compare. This is strong. So this is weak. Okay, so this is strong. So this is automatically weak. And so this is strong. So this reaction goes forward. That is why acid liberate CO2 from NaHCO3 solution. This is how you will do. Okay. Phenols, if I talk of just phenols in general, phenols do not give this reaction. If you react with NaHCO3, PHONA plus H2CO3, if you'll do the same thing, this reaction goes backward, back, forward. Okay. But if there are two nitro, from 2 nitro and forward, then they will start giving this whole reaction. PHONA, NO2, NO2 plus H2CO3. From 2 nitro and more, 2, 3, this becomes forward. Okay, please remember this. And yes, phenol reacts with Na2HCO3 and form NaHCO3, but not any further. Is that absolutely clear? If you want, please take a screenshot. Is it coming on your entire screen or not? I'll reduce the size. Now take a screenshot. Okay, this is important. I hope all those who wanted to take screenshot are done. So among the following, the total number of compounds soluble in NaOH. Now soluble in NaOH, matlab they have to be reacting. Okay, here I have not written, I'll write here. So whichever acid should be stronger acid than water. That is the key, right? No. Acid, yes. Now see, OH attached to sp3 is alcohol. This is not stronger. This is just almost equal. So no. Phenol, yes. Acid, yes. Hydrocarbon, no. Phenol with electron releasing group, then also yes. Because pK of phenol जो है वो roughly 10 है. Even if some releaser is there, it will become 11 or so. but still 15.5 set is going to be greater. No. So 1, 2, 3, 4. Answer is 4. This type of question could be asked by this concept. Okay. Then it comes carboxylic acids. Same concept is applicable to carboxylic acid also. But remember, strongest is formic, then benzoic, and then comes the other carboxylic acid. Same thing, electron withdrawing will increase, electron releasing will decrease the K. There is ortho effect, that is all ortho substituted will be strongest in their comparative set. Ortho substituted benzoic acids will be stronger in their comparative set. Okay, irrespective of whether the group is releaser or withdrawing. In case of hydrocarbons, we have terminal alkynes which are acidic. Okay, please remember this. It is not more acidic than water, but it is more acidic than ammonia. So it reacts with NNH2. But if you want to react it with water, NaOH, then it will not have this reaction. Okay. Again, I have put the same thing here. Which acid will react with NaOH and which with NHCO3? Take it as a practice question. Okay. Everything is given. Out of these, which will react with NaOH and which will react with NHCO3? You know, you don't have to go for these two, but compare these. So if I say, यहाँ मैं लिखूं NaHCO3 और यहाँ मैं लिखूं NaOH, तो phenol with NaHCO3, no. With NaOH, yes. RCOH with both. Benzoic acid with both. Acetylene or terminal alkyne with none. Water with none. Right? This is how you will take. Again, discuss the same thing. Same when it reacts, when it not. Coming to this question. Yes, Abhishek, just wait for class to end and then you can ask. I'll ask you. The correct acidity order of the following. So as I said, first you check, okay, phenol, chlorine OH, 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 COH, CH3COH, COH. So by writing this much, it is clear that third and fourth will be better acid than 1 and 2. This is going to be true because phenols will be weaker. So anything in which first two position pe I see 1 and 2, I will discard that as an option. Ye to ho hi nahi sakta. They can't be stronger. Right? First thing first. Now between 3 and 4, of course, fourth is having electron releasing group. So K will go down. So 3 should be stronger than 4. Seems to be correct. This is electron withdrawing group. So 2 should be stronger than 1. Answer is A. Okay, so direct questions could be asked. Oh, this is not that direct. These questions are not that direct. For these to understand, you have to be very, very clear with this NCERT page. This is an NCERT page. As per my NCERT, it is 372 page number. This and just one page here and there, 373. These 2 pages are like khajana, is like, what should I say, lot of source of questions. All these read properly. Which is stronger, which is weaker, why, how. Okay, here pKs are mentioned. Read OCH3 is stronger or nitro is stronger. And from there, this question was asked in JEE. All things are almost there in our NCERT. So coming back to the question that we were discussing, this one. So as we have seen there, common thing is COH, 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 and COH. So we'll just leave the COH. And we'll see the effect of other. This is SP Padosi, SP2, right? SP2 but with an electron releasing, and this is SP3. So this is going to be a plus I for sure. ये plus I होगा, है ना? Because what we know is formic, then benzoics, and then the RCOH. So among this list, this is going to be the poorest of all, and thus D option is gone. Right? This is how you will eliminate the option. Now, if I compare others, SP has to be strongest. So I will eliminate option A. Right? SP has to be the strongest electron withdrawing. So 1 has to be on the top, 4 has to be on the last. Now 2 and 3 is something which will require your NCERT reading, that vinyl or OMe, which is acting as a stronger electron withdrawing group, and vinyl is acting as a stronger electron withdrawing group. So if vinyl is acting as a stronger electron withdrawing group, so next is 2, then 3, and then 4. So answer is B. Okay. This is something which is very much NCERT based. Please read NCERT as many times as possible. See, this is question number 30. Let's see. I must have added its answer. 30. Answer is B. Answer is B. Okay. With respect to the compounds 1 to 5, choose the correct statement. Again, you have to find the acidity. So you remove these, form anions. Compare the stability of those carbon ions. More stable those carbon ions, better will be the acidity. That is how it should be solved. Okay. And you will find the answer in the end. Right. So this theory I am ending here at page number 31. I'll remember. I'll share these notes tomorrow, and I'll share reaction intermediate notes today. Okay. Ultimately, this I will share again tomorrow, because I'll do from this page number basicity. I'll discuss more. Right. So currently I'll entertain doubts. If anyone has any doubt, those please continue to be in the meeting and raise your hands, and others can leave. Abhishek was there. I asked him to hold. Is there anyone with any doubt? Please raise your hand. Yes, Abhishek.
Ma'am,
Yes.
ma'am, I have a doubt on the reaction of that carboxylic acid. In this we can see that the C double bond O and OH. In this case, OH has a hydrogen bonding with the carbonyl. So at that case, I think the ring formed by hydrogen bonding should be more stable than the RCOOH should be less acidic, no?
Let me go to what you are saying, where I have written, and then you ask, because I cannot answer you specifically when I am not clear. Let me go to the H bonding page. This page?
Yes, ma'am.
Abhishek, here you asked something? Okay.
Huh.
Which portion here?
Uh, at the case of, I think previous page it is. This is not that page.
Okay, let me find the other page. Here.
Yes.
Which one? Example 2?
Yes, in the example 2.
Now you tell again. Now I can better understand the question. You said
I said that the yellow marked hydrogen is doing an hydrogen bonding with the oxygen, that carbonyl oxygen.
this one.
Yes, yes.
No, that is
Then,
not the case. That is not the case. Never. Okay, in carboxylic acids. See, in carboxylic acids, the H bonding which is found is of this intermolecular nature, not of intramolecular nature. This is 4-member strained ring with 2 sp2. They are not close enough to form such bonds.
that means due to angle strain, they can be stable.
They cannot form the bond. They can be stable, they cannot form this H bond.
Okay.
And this H bond, you must remember, because in your chapter colligative property, benzoic acids exhibit Ventov factor 2 due to this intermolecular H bonding.
Yeah, I remember that.
So that there you saw na intermolecular H bonding hoti. It do not show intramolecular H bonding. Right? Okay.
Yes, ma'am.
Anything else, Abhishek, from this slide?
No, ma'am. That was the only doubt I got.
Okay. Others, if there is anyone else who need to ask anything, they wait and raise your hand. Others can leave. There was someone named Akhil also, I remember, whom I asked that please wait, in the end you can ask the doubt. I think, I don't know whether he's in the meeting or left. Okay, no one. I'll wait for 2 more minutes or else then we'll end. Okay. All those who have no doubts, you can leave kindly, no problem. Yeah, good night. Good night. Bye-bye. Yes, one hand I got is, I think, Prajnadeep. Prajnadeep, is there anything you want to ask? Please unmute yourself.
Ma'am, how to determine the hybridization of carbon?
Beta, I could not listen you anything. Your voice is continuously breaking. Can you repeat?
Ma'am, how to determine the hybridization of carbon?
I could understand how to determine, and then middle part is missing, of carbanion. That middle statement repeat.
The hybridization, ma'am. It can be
Hybridization.
to sp2.
Is it hybridization of carbanion you are asking? Show a thumbs up if I have got the right question. Hybridization of carbanion. How to determine hybridization of carbanion?
Yes.
I guess you said yes. Okay. So, hybridization of carbanion, Prajnadeep, as per your chemical bonding only you are determining. Right? Like if I say CH3 minus, so there is a lone pair. So carbon, hydrogen, 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 and one lone pair. So 3 bond, 1 pair, total 8 electrons there, no resonance. So I'll say sp3. Okay. But when this is a situation, but this lone pair can participate in resonance. Now for resonance, this has to be in unhybridized if possible. Hybridized orbital if possible. Of course, it is not a rule. Right? Yesterday only we saw that in aniline nitrogen is sp3, phenol oxygen is sp3. So that is not a rule, but in carbanion, yes, if possible, it has to be in unhybridized orbital. So carbon, hydrogen, hydrogen, single bond CH2 CH double bond single bond CH2 double bond CH2 like this, right? So now this anion has to be part of resonance. 1, 2, 3 sigma. So it is sp2 and this is in p orbital, unhybridized p orbital. Okay, that is how, Prajnadeep, you have to find the hybridization. Okay. Okay, so anyone else, if has any doubt, they can stay back, others keep leaving. No one? Fine, so I'll end today's meeting. Tomorrow I'll continue with basicity. Okay, these topics are very heavy, they are very exhausting. So yes, it will take some time. So tomorrow I'll take basicity and tautomerism, right? Chemistry in everyday life on Thursday then. Okay, everyone, good night, take care. I'll share the notes with central office. They will forward you. Good night, everyone. Akila, you rose your hand. Yes, what is it?
Ma'am,
Yeah.
ma'am, like, how do we know when to use like plus h greater than plus r, plus h greater than plus I, like that?
That is a general thing, Akila. Like electronic effects, we say, then always we say resonance dominates over hyperconjugation and dominates over inductive. This is a general conditioning. This is always true with an exception of. Exception is only one, that is halogens. I write instead of Cl, I'll write halogens. Only in halogens, minus I dominates over resonance. Right? Otherwise, always any type of resonance is thermodynamically more dominating than hyperconjugation and then the inductive.
Yes, ma'am, but like plus r, minus r, which will be greater? Like,
That you have to go for a bit at yesterday's lecture. If CH2 double bond, CH single bond, any group with a lone pair, then it is a plus R. Right? Revise your lectures जहां पर तुम्हें minus R plus R 11 starting में बताया हो. If group is withdrawing electron like this, then this is a minus R group.
no, ma'am, that's not my doubt. Like plus r is greater than minus r, greater than plus h. Is there something like that? Or
A group, no, a group which is exhibiting plus R will not exhibit minus R at the same time. So you cannot compare, you won't need, there is no data to compare such effects. Even if something is capable of exhibiting both, will exhibit one at a time. Na? For example, a ring is capable of exhibiting both, but with carbon ion, it will exhibit minus R.
no, ma'am, what I was trying to ask is like plus r, plus h, minus h. Like plus r greater than plus h or plus r greater than minus h, something like that.
No, where to compare? I am not getting that point of yours, that where do you want to compare? There is no generalization that this in general will be dominating. Where
Ma'am,
do you
again,
give me
two
example.
compounds will be given. In one NO2
No,
will be.
tell me those two compounds. Because hypothetically, I cannot answer. I could not see anywhere I'll need what you're asking, or anywhere I have a data where I can comprehend what you're saying. So what?
Ma'am, for example, benzene ring attached to COH and benzene ring attached to NO2.
OH and benzene ring attached to
NO2.
NO2. Okay. So what do you want to compare?
Acidity.
This is better. This is not even an acid, as this has H attached to oxygen.
Okay, ma'am.
Right? That you cannot. But in general, if you want to, if I could, I don't know whether I have got your answer or not. But even if I want to say, then yesterday we discussed first who is involved in resonance and then how it is, numbers are there. That factor you may consider if you want to check stronger minus R group or a minus R, weaker minus R group. Like what I want to say is, for example, if I have, say, this, and if I have this, we say na this resonance energy is greater than this. In both,
Yes,
this
ma'am.
heteroatom is a plus R group. But how you decide this is better? Less electronegative is a better donor.
Yes, ma'am.
So that way electronegativity sometimes can help you.
Okay,
Right?
ma'am.
That who is bearing the charge, who is withdrawing the electron, such groups could be like COH, right? And versus I have SO3H. So I'll say this is a better minus R as I have 2 oxygen to withdraw and 1 oxygen to withdraw.
Okay, ma'am.
Somewhat like this. I hope it makes sense to what you're asking, right?
Yes, ma'am. Thank you, ma'am.
Okay, beta. Thank you.